that guy? Good. Cyclopentane. Okay. So it's cis. So remember, when you have a ring, sometimes you see it kind of represented like this. Sometimes you see it with the wedge and the dash. Now, looking at that, you can pretty easily see that you have that plane of symmetry there, right? So this is an internal plane of symmetry, internal mirror plane of symmetry. And this likes to be defined by a sigma. You ever notice, like, sigma is just very popular for everything, it seems, in organic chemistry. So sometimes you might just see in your book or on an example problem this little and have a little sigma right by it. So that's just showing you that you have this internal mirror plane of symmetry in cis, in the cis conform. But you know with cis you could also have trans, right? So let's draw the trans up here and see. What about that one? So with that one, we would have this. Okay. So this would be our trans. Two. Dichloral, cyclo. Okay. So now looking at that, does that have an internal mirror plane of symmetry? We thought, can I go down here? Okay, no, I'm not the same now, right? It's not like that one. So at that point, if you had a question that said, is it achiral or is it chiral? First, you could kind of look at that, and if you quickly see the mirror, you quickly know it's achiral. If you don't, then think, okay, let me think of its mirror image, and let me see if it has an enantiomer, and check it. So now, we're going to think, okay, let's draw the mirror. I always have to step back and make sure. Okay, it is a mirror. All right. So at that point, we look at it, and you can think, all right, can I pick it up? Can I place it on top of here? Is it non-superimposable mirror image? And again, this is the kind of thing that might be hard to see. And if it is, you can make your model, even of rings. You still can do it. You can make a model and look at it. But in that case, you do have enantiomers here. You have two enantiomers here. Okay. Has an enantiomer. And whenever anything has an enantiomer, then you know it is chiral. This one is chiral. That one's chiral. That one was the achiral. So notice you could have these two different stereoisomers, cis and trans, those geometric isomers, but one can be achiral and one can be chiral. Okay. Okay, so now there has to be a way to name these different configurations. So you say, okay, I have these two enantiomers, but how would you know what they were just by saying trans 1, 2? You wouldn't know which one you have, right? So there has to be a way, and of course, there's a way created to name these enantiomers. And it will go by adding an R or an S to the beginning of our name. So it is called R and S configurations. We're going to take it through step by step. This is another naming process that has rules that apply. Okay, so we're going to go through the rules, and then we're going to go through examples. In case you wanted to know, the R and the S comes from Latin, because I have been asked this question for rectus, which means to the right. Does anybody know Latin in the room? No, I don't.
We all look at
And S is sinister, or to the left. Okay? So, it will help you as we go. One way, you're going to look at naming and you're going to be looking if these rules apply to the right and the other way to the left. But your R means to the right, so that's nice, right? R, right. So that will help you remember that. Okay, so for example, to kind of apply this to biology, for you biologists out there, which I feel most of you are. Okay, so this we're looking at alanine. We're looking at the amino acid alanine. And this you'll learn much more about if you take biochem. But there's going to be a natural and an unnatural configuration, if you will, for alanine. And the natural configuration, one of them, is going to be biologically active, but the other one is not. So you need to know which one is which, right? We need to have a name for it. So thinking about, we'll put down here, this is your natural. Over here, your mirror image. Okay, so notice your mirror image. This would be your unnatural. And looking at that, you would think, okay, we're looking at that carbon. So if we say, we are saying that there's an enantiomer, we know that this one is the carbon that we would look at here and think, does it have the 4 different groups? Yes, it does have 4 different groups around it. That was our chiral compound, it has an enantiomer, okay? So now, you need to have a way to distinguish this. We'll leave that up there and we'll put up after we do our rules. So the rules for RNS are the Kohn-Ingold-Krylov convention. There's always a name for everything too. So these are going to be the rules that we're going to need to make in order to determine if it's going to be R or S. Okay, so 2 different configurations. And now we need to talk about how to make them. So number 1, you have to assign a relative priority to each of the groups that are around that chiral carbon. So assign relative priority to each group bonded to the asymmetric or the chiral carbon. Atoms with higher atomic numbers are going to have higher priorities. So this is how you're going to do that. Atoms, higher atomic numbers, have higher priorities. Okay, so this is where if you have that periodic table with you, it could be helpful to have that out so you can kind of follow along. So you're remembering your atomic number and which one's going to be higher. I'm going to leave this one up here, but I'm going to put a smaller